This is a presentation by me, Eric Binnendyk, of a paper by Dan Tang, Liu Tang, Rui Dai, Jingwen Chen, Xiong Li, Joel J.P.C, Rodrigues, called MF-Adaboost, LDoS attack detection based on multi-features and improved AdaBoost. At the end, I will give feedback about the paper and how the research was conducted. This paper is about network security from denial of service or DOS attacks, and the research uses a predictive method called AdaBoost to stop these attacks. Traditionally, a DOS attack is when a particular computer in a network overwhelms a router, causing it to malfunction. DOS is short for denial of service attack. It usually uses a botnet to overwhelm routers and cause them to drop packets, which in turn can paralyze the entire network. Usually it involves just sending out a really large number of packets. There's also a special type of attack called a low-rate denial of service attack, or LDoS for short, that sends packets at a low rate, but specifically coordinated to disrupt the routing protocols. And as you can imagine, LDoS attacks are harder to detect than just plain DOS attacks. Now, to use a machine learning model on network traffic, we have to explore the data to extract significant features from it. The traffic to a node is treated as a time series, which is basically a distribution of frequencies at which packets arrive and how they change over time. Now, mathematically, the time series is just a distribution of a random variable, so you can perform the statistical tests on it, like mean, frequency, variance, skewness, kurtosis, all that kind of stuff. Signal processing approaches have been used previously. So the authors describe several related instances of work along the same lines, including signal processes approaches, which are useful because network traffic is a time series. Chen et al. Proposed two statistical features for the time series to help detect LDoS attacks, which were the Fourier power spectral entropy and the wavelet power spectral entropy. Agrawal et al. Proposed a method for detecting attacks that worked in the frequency domain based on the power spectral density of a time series. Wu et al. Proposed a method for filtering out the attack streams based on spectral analysis. Yue et al. Proposed a method based on the wavelet transform in a neural network to extract certain coefficients from a time series that distinguish LDoS attack flows from the non-attack traffic flows. So in the model, each network traffic scenario is converted into a time series. For the descriptive features, several statistical measurements are taken for both TCP and UDP traffic. Out of all those features, we need to find the ones that will be the most useful to learn. This can be challenging and is sometimes done with neural networks, or by consulting a domain expert's advice. But in this paper, the authors just measure the correlation between each feature and the target feature using the chi-squared test. So in the formula you can see here, we have the output labels for the data, whether they're an attack or not an attack. And we also have the features, and we're seeing whether the feature is, the range of the feature, the values of the feature are correlated with whether or not that particular data is an attack. So they have to give each label a numerical value. I think they use 0 or 1 as their values, or maybe -1 and 1, because 0 and 1 wouldn't work if they're dividing by the data label. So anyway, calculating these chi-squared values gives us a good idea of which features will be the most useful. And we add the most optimal features as our model's descriptive features one at a time. And you can see on the right, there's a graph of the scores of some particular features that the authors measured, including the ratio, the mean and variance of TCP and UDP, the covariance, the total values. Now, the predictor that the authors introduced is an ensemble learner. The algorithm is based on a boosting algorithm called Adaboost. As a boosting algorithm, we have a bunch of learners run in succession, and each one is trained specifically on the data that the previous learners got wrong. Now, the individual learners are called weak classifiers, and the final prediction is a weighted sum of their outputs. You can see the formula has the weights alpha, and each of the weak classifiers are the h sub t. Now, the more errors the classifier makes, the less weight we'll give it in that weighted sum. You can see the precise formula for the classifier weights involves natural log, and it so conspires that if more than half of the predictions on a given weak learner are errors, the final model will actually be biased against it, and it'll have negative weight. With each classifier, we train specifically on the instances, or specifically biased towards the instances that we missed using the previous classifiers. In fact, we assign each data point a weight, and the more it's been predicted incorrectly, the more the current classifier will be biased toward it, weighted towards it. You can see the formula for updating the weights W based on the value Z, which was the Z was the previous predicted value, and WT was the previously predicted weight. So in this research paper, the authors use a variation on the Adaboost algorithm called MF-Adaboost. In MF-Adaboost, the formulas are changed slightly so that it has a more balanced distribution of weights and a smoother method of updating sample weights. As a result, MF-Adaboost is better at adjusting its parameters smoothly when the features of the network traffic change gradually with time. And you can see the formula for MF-Adaboost uses the new weights S and the modified weights S of t, and the original weights are W of t. And it calculates the updated weights based on the original weights. So yeah. And these are the weights used in training. So it basically has a slightly different bias towards which instances of data each of the weak classifiers will be trained on. Here you can see the pseudocode that the authors used for the three algorithms: the MF-Adaboost algorithm, the training of the detection model, and the detection itself. You can see we have the sample data, the number of weak classifiers, and we output the strong classifier. Then we have the training set, and we have the feature set, and we output the optimal feature set. And for the third one, we have the optimal feature set, and we have the classifier, which has already been trained, and we output the detection results. So to test the model, the authors set up two different experiments. First, they simulated network attacks using the NS2 network simulator. To their model, they added nodes which simulated background traffic, as would be present in a real situation. You can see the network model they used to the right, the top right, and they simulated 3 different attacks, each specified by different periods, durations, and attack strengths. You see the attack, the interest, the request flooding comes periodically. It doesn't happen continuously. That's what makes the attacks low rate, and that was what makes them harder to detect. And so it happens periodically for a certain duration. They also conducted 3 experiments on a testbed platform, which is basically an isolated system that uses all the same networking hardware and software as the real world. You can see the network they built for the testbed on the bottom right. They also did 3 experiments on the testbed platform. For all of their experiments, the weak classifier used when training the Adaboost algorithm was a naive Bayes classifier, and the entire algorithm used 100 of these, 100 weak classifiers. For the NS2 simulator experiments, the average detection rate was 94.05%, and for the testbed experiments, it was 97.06%. Depending on the period, duration, and attack strength, the 3 defining features of the attack, the optimal number of features for the model to learn about the traffic was different. For the NS2 simulations, the optimal number of features took the values 23, 5, and 7 for the 3 different experiments. But on the testbed, the optimal number of features was 15. The proposed detection method performed better than other methods. Such as multifractal, BP neural network, and PSD, which they also tested on the same testbed. It had both a lower false positive rate and a lower false negative rate than those 3 algorithms. So here are the detection results. You can see that most of the incorrect classifications are right on the boundary as the attack starts or right as it ends. This makes sense because half of the time when those measurements are taken, the attack has started. But the other half of the measurements are taken when the attack isn't going on. So the data is mixed. For the conclusion, the authors just summarized their entire methodology in a single paragraph. And the process of their research, including how they used chi-squared for feature selection, how they improved the Adaboost algorithm, and how they tested on the NS2 and testbed platforms. Yeah. They also go into possibilities for future research based on evaluating their model on a real network, and also a plan to use their model to separate attack traffic from legitimate traffic when an attack is going on, filtering the different attack flows, filtering the different flows of data. And now for my evaluation of the research. Overall, I think the research is conducted quite well. The paper was also written quite well, although it could be improved in a few ways. The authors started by giving a detailed background of previous algorithms and previous research in the area of predicting network attacks, describing such methods as the wavelet transform, talking about statistical features and whether to find them by hand or use deep learning, as well as the theory of time series and boosting algorithms, and a frequency domain analysis versus time domain analysis. The algorithm and the pseudocode are both explained in detail with mathematical formulas included, which is good. It's easier to replicate that way, and it goes into the theory behind why the algorithm works so people can gather insights. And much of the paper is spent providing a background to understanding the algorithm. They also gave realistic testing scenarios, taking into account things like background noise. Now, that being said, there were a few issues with the paper. Much of the language was quite technical. And many of the technical terms weren't exactly defined. Like at the beginning, they were introducing the theory behind some of these detection methods and time series analysis, and they were talking about the eigenvalues and the energy of a distribution, terms which they never actually defined. They never defined time series either, and it was hard to understand exactly how they converted the traffic flow into a distribution. They also used target labels on the data as numeric values, as I pointed out earlier in their formulas, without mentioning how they converted the categorical features to numeric ones. Like they didn't explain when they were describing the Adaboost algorithm, they didn't explain what the target features no attack and attack or false and true, what numbers they converted to. I wasn't sure whether it was 0 or 1 or -1 or 1. The recap in the conclusion, I think it was somewhat weak because it started by recapping the entire process, but not in a very condensed way. They still kept in all of the details, and the entire recap was a paragraph of about 30 lines, much of which was just spent redefining the same terms used in the paper in a kind of meandering writing fashion, with the main point of the recap coming in only in the last few sentences, which made it feel slightly rambling. This is followed by just a few sentences giving a direction for future research. Now, the ideas for future research were interesting. The plan to use the algorithm to filter LDoS attack flows from legitimate traffic. That sounds like an interesting direction of research. And if possible, it would have been nice to hear how they plan to do that. But overall, I found this paper to be quite interesting, and I found the research to be quite well presented and well thought out. So that's the end of my presentation. Thanks for listening to it all. Overall, I think this paper was very interesting, and I learned quite a lot about applying predicting algorithms to network security. If anyone has any questions about what I just presented, feel free to start a discussion on Canvas. I look forward to hearing any questions you might have.